Hello everyone, I'm Professor Harrison, and welcome back to our module on matrix algebra for finance. Today we're going to be covering matrix addition, subtraction, and scalar multiplication. We're following Ruth, a PhD student building out her matrix-based methodology for her dissertation. Today she's working through these operations with Victor, her closest colleague in the program. She walks up to her chalkboard. In the previous video, we worked through vectors as a special case of matrices, along with three operations on them: the dot product, the norm, and projection. So we have the language of a single row and single column matrix, plus the operations that connect them. What's missing now is the basic arithmetic for full matrices. We can write down a matrix, but we haven't been able to define what it means to add two of them together, to subtract them, or to multiply them by some number. These end up being the simplest of all the matrix operations, but once we have these tools in our back pocket, we'll be able to move on to more complex topics. Let's make things concrete first. We'll set up a small portfolio example. Imagine a fund family that runs two funds. One fund is a growth fund and one is a value fund. Each fund holds shares in three assets. So how do we represent this with matrices? What we're going to do is position the matrix so that the rows are the three assets and the columns are the two different funds. Each entry is the number of shares that one fund holds in each asset. That single matrix carries the entire allocation across both funds at one moment in time. We'll call this matrix P, and it'll be our position matrix. Let's suppose it looks something like this. Asset 1, the firm holds 200 shares in growth and 100 in value. Asset 2, 300 in growth and 400 in value. Asset 3, 100 shares are held in growth and 200 are held in value. So P is a 3 by 2 matrix. Yesterday's position matrix Q is slightly different, since the funds traded between yesterday's close and today's. Yesterday, asset 1 was 150 in the growth and 100 in the value. Asset 2 was 350 in growth and 350 in value, and asset 3 was 100 shares in growth and 250 in value. Q is also a 3 by 2 matrix. The first thing we want to know is what trades happened overnight, the difference between today's positions and yesterday's. Matrix subtraction will tell us exactly that. Subtraction works entry by entry. The entry in row I, column j of P minus Q is just P sub ij minus Q sub ij. So for example, today minus yesterday for asset 1 in the growth fund is going to be 200 minus 150, which equals 50 shares purchased. Asset 1 in value would be 100 minus 100, which equals 0, so there was no trade. Then for asset 2 in the growth fund, 300 minus 350 equals negative 50, meaning that the growth fund sold 50 shares of asset 2. Continuing down the matrix, and you end up with a complete trade matrix T, which equals P minus Q. Each entry is positive if shares were bought, and negative if shares were sold. There's 0 if there was no trade. One thing that this example shows us quietly is that we're only able to subtract these two matrices because they have the same shape. Both are 3 by 2. Think about what would happen if we tried to end up subtracting two matrices that don't have the same shape. An example of this would be if both funds started trading some fourth asset. If this happened, then the previous day's matrix would be 3 by 2, and the current day's matrix would be 4 by 2. If you tried to line up the entries to do the subtraction, you wouldn't be able to because there's more entries in the second matrix. So what we'd have to do instead is make both of our matrices the same shape. We can take yesterday's matrix and add a row of zeros to the bottom to make it a 4 by 2 matrix. This is effectively saying that neither of the funds held the fourth asset yesterday, and it allows us to now do the subtraction. But without making sure that both our matrices are the same size, there would be no way to do the subtraction. So that's subtraction. Addition is just subtraction with a plus sign, so two matrices of the same shape add entry by entry. So if we wanted to compute the firm's combined exposure over both days, we're going to add P plus Q, and the result is a 3 by 2 matrix where each entry is today plus yesterday's. This gives us the total exposure in some sense, and it tells us how much we were exposed to the positions based on how long we held them. Now let's suppose that the fund family is planning to double in size, and we want to model what the same proportional positions would look like at twice the scale. Here we could just multiply the entire matrix by the scalar 2. Scalar multiplication, like addition, works entry by entry. Every entry of the matrix gets multiplied by the scalar. So 2 times today's matrix P scales every position to twice its current size. So for example, the 200 shares in growth in asset 1 end up becoming 400. The 300 in asset 2 becomes 600, and so on for every single entry. The scalar can be any real number. A scalar of 0.5 would represent halving the size of the fund. A scalar of -1 would flip every position into a short of the same size. The shape of the matrix doesn't end up changing. So with addition, subtraction, and scalar multiplication defined, there are a few properties worth naming. They look a lot like the properties of regular arithmetic. Matrix addition is commutative. A plus B equals B plus A. The order doesn't matter. It's also associative. A plus B plus C you can group however you like. A scalar multiplication distributes over matrix addition, so a scalar C times the sum of A plus B equals C times A plus C times B. These are easy to verify entry by entry, and they're not much of surprises. They're worth knowing because matrix multiplication, which we'll cover in the next video, ends up being a lot less well behaved. Ruth steps back from the chalkboard. Victor follows the operations. He asks whether all these rules are going to extend naturally into multiplication. She tells him not quite so much. There's a bunch of different rules, and that's where things are going to get interesting, and they're going to work on it in their next session. These 3 operations are the bookkeeping pieces of her framework. Every time she combines 2 sub-portfolios, every time she rescales an exposure, every time she takes a difference between 2 periods, she's using exactly these operations. They aren't the centerpiece of the dissertation, but they're what makes the centerpiece work. So that's matrix addition, subtraction, and scalar multiplication. 3 operations that all work entry by entry. The conformability requirement applies to addition and subtraction. The standard properties of arithmetic carry over without surprises. These are the bookkeeping pieces that the rest of matrix algebra will rest on.